the final remaining theorem that I want to discuss with you in this section is theorem 4.5.2. And it says, for any integer n, the floor of n divided by 2 is either n over 2 if the n is even, or it's n minus 1 divided by 2 if n is odd. Well, let's try to understand what this theorem is saying before we dive deep into the proof. So suppose I pick an integer n, and suppose I pick the integer to be 8. Then according to this theorem, if I want to know the floor of 8 over 2, then all I have to do is divide 8 by 2 and get 4. That's the case number 1 of the theorem. And is that true? Well, the floor of 8 over 2 is the floor of 4, and yes, the floor of 4 is 4 itself. So the theorem seems to have worked. Now, in the case when n is odd, for example, if I choose n to be 13, then according to this theorem, if I want the floor of 13 divided by 2, oops, this is supposed to be a floor, the floor of 13 divided by 2, then all I have to do is subtract 1 from 13, and then divide the number by 2. So basically 12 over 2, which is 6. Well, is that true? This is what the theorem says. Let's calculate with another strategy. 13 divided by 2 is going to be 6.5. And what is the floor of 6.5? The largest integer that is smaller than or equal to 6.5 is 6. So again, the theorem seems to have worked. So it seems that this theorem is in fact true. And now we need to try to prove the theorem. So here's how the proof is going to work. It's going to have two parts, basically two cases. A case where n is even and a case where n is odd. This is what we kind of discussed in the previous section when we described the method of division into cases. Now if n is even, then by definition of even, n can be written as 2 times k, where k is some integer. So therefore, n over 2 is going to be the same thing as 2k divided by 2. Remember, n is 2k, so I can plug that into the expression for n. And then, since I have 2 on the numerator and 2 on the denominator, I can now reduce the expression, reduce the fraction, and end up with the floor of k. But remember, k is an integer. We said that over here. And that is true because of the definition of the word even. So the floor of an integer is the integer itself. So that means that the answer is supposed to be n over 2. Why n over 2? Remember, n is 2k, so if I try to isolate the k in this problem, I would be required to divide by 2 on both sides. 2's cancel out, and I get k is equal to n over 2. So k is n over 2. And this shows that the first part of the theorem actually holds. So we basically finished the part of the theorem where n is even. Now we have to look at what happens if n is odd. And we'll take a look at that here. If n is odd, then the definition of odd leads me to the conclusion that there exists a k that is an integer such that n is equal to 2k plus 1. And again, since I want to eventually have this ready to go, I'm going to solve for k to end up with k equals to n minus 1 over 2. I'll need that in the future, so this is kind of a comment at this point. So that's why it's written in italic form. So therefore, what would happen to my n divided by 2? Well, n is 2k plus 1, so I'm just going to substitute it into the numerator. And when I do that, I'm going to end up with 2k plus 1 all divided by 2, which means I can separate the fraction into 2 pieces and divide out the 2 on the first fraction to end up with the floor of k plus 1/2. But remember, k is an integer. An integer plus half has a floor of the integer itself. Try it out to yourself. What is the floor of 3.5, for example? Or the floor of 5.5? Or 7.5? Remember, you're taking an integer first, and you're adding half a unit to it. The floor of all those numbers are going to be the k itself, the integer itself. But what was k in the first place? K is n minus 1 over 2, so that means we can now substitute it. And that's what we wanted to show in the theorem. So since it holds for the first case, and it holds for the second case, the theorem is true in general, and we're basically finished.